it was a couple of years ago, the Yuma Agriculture Water Coalition put together this report. And we were called in because we had some databases that were relevant to this report, and we shared some of this data with them. But in this process, there were data gaps that were identified. So I want to start with the fundamental questions you ask yourself in irrigation. And they are, when do I irrigate? That's timing. How much water do I apply? And how do I operate my system to achieve that required depth? And these are all things you can vary. And we approached it from the very beginning in this manner. Now, irrigation may seem like a simple thing. You open up a channel and water flows out, but there's lots of things going on. There's advance, there's infiltration, there's recession. Fortuitously, irrigation is a physical event. And anything that's physical, I can put math on it. And this is the math we use. This does a very good job of describing surface irrigation. Essentially, it's a truncated momentum equation where we drop the terms for convective and local acceleration because they don't contribute significantly to the irrigation event. And we calibrate these models under field conditions. This is some of our calibration experiments. And then we validate them with independent data sets, not the same data sets. And just an example of some of the validation, this is irrigation advance. The pink line would represent what our model predicted, and the yellow dots would represent what's observed in the field. There is some variation, but this is much better than I anticipated. We grouped the soils by texture, but even within those groups, there's some variation. So you will see some noise, but we were quite happy with our validation results. A little bit about efficiency. To hear everyone talk about efficiency, and there's countless expressions for that. I want to distinguish them because I'm going to throw these terms around, and I want you to be clear what I'm referring to. Irrigation efficiency is the evaporative transpiration of the crop relative to water applied. Irrigation efficiency beneficial use is water used beneficially. That would be water used for the crop ET, water used for salt management, water used for tillage, relative to water applied. Application efficiency is the required depth divided by water applied, which is essentially equal to this within a single irrigation event. And then there's finally water use efficiency, which is production relative to water applied. And here shows some of the results from our model, and I just want to make one point here. Within season, for the produce, within season, after we cultivate and set our bolas, we're incredibly efficient. This shows the application efficiency. This shows distribution uniformity. If we let in about 40 gallons per minute into a furrow and cut off irrigation after 80 minutes, you can see we're better than 90% efficiency. So within the season, we're there with drip irrigation. We're just right there. We're incredibly efficient with our short runs and our trapezoidal bolas. But on the other hand, if you use Colorado River water, theoretically you have a leaching requirement of 20%. We do not get a leaching of 20% here. So you can surmise, just from this hydrology data I collected, that within season, we're going to be a slightly salt loading enterprise. Same thing with sprinklers. We use sprinklers for stand establishment, but for some crops, the baby and the spinach, we do it year long. Similarly, I've calibrated models. Here's some of the models. This is a little simpler. It's just a solution, a numerical solution of all the mass and energy balance equations on a pipeline. We've gone to the field, we calibrated and validated these models. And you can again see predicted and observed hydraulic lines across these fields. So we have good models, and in season, we're very efficient. But during this process with the Yuma Agriculture Water Coalition, they identified several data gaps, and many of them are associated with water beneficially used that was not consumptively used, that wasn't ET. Pre-irrigation. Pre-irrigations for salt leaching, hasten residue decomposition, and of course to facilitate land prep. You don't want these great big clods, you want to break them down. Stand establishment irrigation, climate modifications in mind, and hopefully we can pick up a little salt management as well. And thinning irrigation. We haven't put the bolas in, the rows are generally open. We soak those beds good to facilitate how quickly and how efficiently our thinning crews can move across these fields. And maybe we pick up a little salt leaching in these events. And what I'm going to share with you today is some specific data from all these events. So here's what we're doing. Essentially, we've been charged with understanding the salt balance over the whole cropping system, from the vegetable season through the rotational crop. And I'm going to turn over to my colleague, Dr. French now, who's going to share with you some of our methodologies for collecting the atmospheric data.
Well, good morning. Charles has just explained that what we're trying to do is close the water budget, and my role in this is to compute or measure the evapotranspiration part of the water budget. So the inputs are irrigation, precipitation. We know what the irrigations are in the area, in the Yuma area, but we don't know accurate numbers of soil storage, deep percolation, surface runoff is minimal. But those last two items, evaporation and transpiration, are majority of the water lost through the water cycle and the most difficult to measure. And the graph at the right here illustrates seasonal variation in the evaporation and transpiration for crop. This is not lettuce, this is cotton, but this data that we've collected for and accumulated for years in Maricopa just to illustrate how variable they are from the day of planting here to the end of season, about 160 days later. These spikes are evaporative losses where the water is exposed at the soil surface, and the green curve represents the basal evaporation. So what we want to do is measure and discriminate between those two so that we can get an accurate water budget. Well, really, I'm not sure what growers in Yuma use for their irrigation numbers, but in the scientific literature, I have to say that it's pretty skimpy. Gravimetric data that's illustrated on the left-hand side from Erie publications is from the early 1960s in Mesa. It was a long time ago. They're excellent data, but if you look at this for lettuce, there's just not a lot of discriminatory information as you go through the growing season, and clearly we can do a lot better than that. The other way to do it, and it's been supported by the Arizona Weather Network, ASMET, yes?
I just got a question on your timelines on both of these. It's kind of hard to see back here, but I'm wondering what your start and your end date is on both of those graphs, what your bottom grid is.
Okay, so the time scale on the graph on the left starts in September and ends in December, and these are 2-week periods. And then on the right-hand side are days past planting, so 0 to 180. So these are, if you look close at the publication there, the Erie publications, it'll give you consumptive water use at 2-week intervals here. And this is the cumulative water use graph here. Seasonal water use is plotted here. Well, on the right-hand side is how we can do crops such as cotton, and we could presumably do the same thing with lettuce if we had similar lysimetry data, but we don't have such data. So what Charles has just described is that we have much better instrumentation since the 60s. We can much more accurately characterize where the water goes. And here are some of the instruments. If you're driving around the area, this is the point of showing these graphs, is to show that there's reason for deploying these rather expensive and complicated instruments. Out here, there's a typical deployment, shows that there are 3 tripods here, the solar panels that provide the power. The main instrumentation are in these two tripods here. This is what's called the eddy covariance station, and this is the net radiometer, and buried in the soil are soil heat flux plates. So to measure evapotranspiration, we have 4 main components, which is net radiation, soil heat flux, sensible heat flux, and latent. And what we really want is the latent heat flux, which gives us the total water used. And these are the components that they look like if you drive by and see some of the fields where they're installed. This is the sonic anemometer, and that's the infrared gas analyzer. And what do the data look like when you collect them? These are typically aggregated at half-hourly intervals, and they give you very fine measurements of water distribution throughout the profile through the near soil profile. This is a daily time scale here. These are the 4 components of the energy balance measured from that station I showed you in the prior slide. and you can very accurately pinpoint where irrigation began, which is illustrated here. You can see that the sudden rise in latent heat, which corresponds to a lot of evapotranspiration. Then when you integrate these curves on a daily time scale, you can get a graph such as this, which gives you daily evapotranspiration across the growing season. So just to summarize, the objectives of the researchers to use the eddy covariance data to get 30-minute data at daily scales and seasonal ET and compute the full water budget. And prior times, we've just used residual methods. This will actually compute and measure all the water components going into the farm, and we merge the analysis to improve our salinity distribution. Another way to measure the evapotranspiration is called the large aperture scintillometry, and we've installed these off of Araby Road here on Smith Farm. And it's illustrated by, it's not so easy to see in this graph here, but it's a 5-meter tower, and on the top of that are these cylindrical bodies that are about 10-pound devices that have an infrared laser. It's a very low power, eye-safe laser, and that shoots a transect across about a mile here between transmitter receivers. And what this allows us to do is integrate the evapotranspiration at larger scales. So the goal here is that we integrate eddy covariance stations at point measurements with these large aperture scintillometry and ultimately satellite data to get a multi-scale estimate of water use across multiple times. Lastly, I'd point out that because of this collaboration, I proposed to the French and Israeli group that launched a satellite called Venus that they target the Yuma region as one of the focus areas. This satellite is now in orbit. It's now started collecting data on November 1st, and it collects data every 2 days, which is very unusual, at 5 to 10 meter resolution. Why is that valuable for growers here? Well, we think this is the way future of satellite data will go. Will allow us to monitor the crop cover at very fine time intervals and predict water use up to 10 days in advance. And this is the target site here around the orange triangle, and we're waiting to see what the data look like. Charles?
Any questions for Dr. French? Okay, I'll resume. We're going to get back to salinity. And usually salinity we measure by electrical conductance. But in addition to this, I'm taking extracts into my laboratories and measuring the complete array of cations and anions. So this is usually expressed as units of decisiemens per meter. But we're also measuring, as with ET, at multiple scales. One of them is we use electromagnetic inductance. We survey fields, we ground truth them with statistically selected soil samples, and we plot maps and grids, kind of like I showed you for the cadmium data. We do this with salinity at multiple depths. And as I noted, we're taking the samples back to my lab, and we're measuring the important cations and anions. One thing I want to comment real quick, one thing that we find high in our soil solutions that we don't find nearly as high in irrigation water, we're talking a couple of orders of magnitude, is carbonates. Where are these carbonates coming from? Well, a teaspoon of soil has over 1 billion microorganisms. And most of them are heterotrophs like ourselves. They consume combined carbon, and they obtain energy by redistributing electrons down a biochemical gradient, ultimately dumping off these electrons on the ubiquitous electron acceptor, oxygen. So these are generating huge quantities of CO2. Some of it diffuses out of the soil, but some of it goes into the soil solution. And you get this carbonate equilibrium, the proportion of which species is dependent on soil pH. In our soils, at pH 7.8, 85% of it is bicarbonate, and a lesser amount is carbonate or carbonic acid. This is important. So this is one of the ions we also keep track of. What happened here? Oh. Now, leaching requirement. For sustainability, you have to maintain salt balance. So any salt you add, and the Colorado River is loaded with salt, and we have 1 ton or 2 per acre foot of water, we have to apply extra water to move these salts through. Let me see this is some pre-irrigation data. I said we're going to talk about specific in-season things. This is pre-irrigation. This is one of our sites. This is salinity at 4 depths, essentially to 4 feet. Each pair represents a foot. And you can see pre-irrigation, we do get some leaching requirement in the surface primarily. And this is another site. This is the Yuma County Water Use Association. Again, we got some. This site's an anomalous site. It's a sandy site. I picked it because of security, but it's skewed towards coarse textured soils to a greater extent than our median soil that we farm for produce. Now, to the extent that we get leaching, fortuitously, we're getting rid of the bad actors preferentially. This shows that we lowered the sodium absorption ratio, which means we're preferentially leaching out sodium relative to calcium and magnesium. And we lowered the chloride. We're preferentially leaching out chloride relative to sulfate. So to the extent that we do get leaching, as we got it in this pre-irrigation event, we're preferentially moving out the bad actors. Little bit about stand establishment. And here, 2.5, 3 decades ago, we made a major leap. We went from subbing, which uses 30 plus inches of water, to sprinkler stand establishment and climate modification, which uses 8 or less. And this was a huge water savings. But when we're running these sprinklers for 2, 3, 4 days, people often comment, how can they use so much water? As you'll see in reality, it's not that much water. Here shows a typical sprinkler irrigation event. We have data loggers, we have sensors at multiple levels, and we've monitored over the irrigation event. The blue lines would represent when the sprinklers are running, and these would be different depths. This is 2.5 centimeters, 7.5, on to 30 centimeters. You can see we fill the top 2.5 centimeters, and once these are full, the next depth gets full. And once those are full, the next depth gets filled. And finally, the last depth gets filled. And it gets filled at about the very end of a 48-hour run. So you've applied barely enough water for the most part and 48 hours of running the sprinklers continuously to refill the soil profile. And these other ones are just to get some climate modification during the heat of the day. And you can see the water goes up, it fluxes up and down, not only to the sprinklers running, but to the evaporative demand of the diurnal daily cycle. Here's salt flux in the soil. Now these aren't ECE, these are bulk salinities, but we can convert them to ECEs, but for this purpose, I just want to show that the salts do flux up and down depending on the time of the day and depending on when the sprinklers are on. So we run them, the salts move down, but we turn off the sprinklers and we get some evaporative demand, the salts can move back up. So even during a sprinkler cycle, we have these fluxes of salts up and down. Let's look at the net salt loading. And this is the water salt load, 1.2, generally 1 metric tons were applied over the sprinkler irrigation event, a bit of salt. But we can see on the front end of our season, that would be September through late October, stand establishment is almost always a salt loading event. We have more salts at the end of that than when we started. There's no net leaching fraction running the sprinklers at the front end of the season. Now, if we move into November, and I have more data, I just haven't listed it on the slide. If we go into November, after our vapor pressure deficits have declined, it is a net leaching event. You can see at the net of a stand establishment sprinkler run, we have less salts in the rooting zone than when we started. So roughly from early September through maybe the last week of October, it depends when the weather breaks, it's a net salt loading event. How about the thinning irrigation? Here's some data from a thinning irrigation. Fortuitously, thinning irrigation does provide us a leaching event. You can see this is in the bed, this is in the furrow. We are moving salts out of the bed, but even after we cease the irrigation, the beds continue to drain, and where do they drain? They drain into the furrow, and the salts in that furrow, the water evaporates, leaving the salts behind. But we are moving salts out of the bed with our thinning irrigation. Now let's look at the whole lettuce crop. This would be before pre-irrigation. This is the top foot here, and then these are the subsequent feet. This would be before lettuce. We got some leaching in our pre-irrigation. And this would be before wheat after lettuce. Essentially, during the produce cropping season, it's a net salt loading event. We're accumulating salts because our irrigation efficiencies are incredibly high. And we predicted that from the hydrology data I showed you earlier in the presentation. And you can see this throughout all the soil depths. This is the other site. This site's a little different. Like I said, this is an anomalous site, very coarse textured. Here we didn't get much leaching in the surface, and we got some in the subsurface where it gets very, very sandy. Now this data is after wheat. We anticipate we would pick up a leaching fraction in the wheat. In this particular case, we did not. You can see the salts even continued to accumulate after the wheat. In this particular site, the error bars show the variation amongst the numerous samples we took. Here's a site with Sudan grass. We're focusing on Sudan grass this year, but I have a Sudan grass site associated with another project. We did get a leaching to the Sudan grass site. We did not for wheat. I have 3 data sets with wheat. 2 of the 3 we did not. One that I did is that anomalous site that's sandy. But Sudan grass, we clearly did get a leaching fraction from the surface. There's one other thing that comes up, though. As I calculated the cation and anions, I went in and did some speciation work. And what it suggests is we're supersaturated with several insoluble minerals in the soil. Argonite, calcite, dolomite, vaterite. We're supersaturated with respect to those minerals. What does that tell you thermodynamically? It tells you that these salts should precipitate out. Thermodynamics dictates that they will precipitate out. And what that suggests is that precipitation may be an important mechanism of salt mitigation than we previously assumed. And in other words, looking at simple mass balance may be a gross oversimplification. Now, thermodynamics dictates that these should precipitate out, but it doesn't tell us when. That's a kinetic question, and I don't have kinetic data at this point. Do they precipitate out in an hour? Do they precipitate out in 5 weeks? Is the time scale in which they precipitate relevant to our management decisions? I don't know that. That's a kinetic question, but we will try to address that in the future. And as Dr. French noted, we are scaling up. We have measurements at the point level, salinity and water. We have measurements at the field level, and through its collaboration with NASA, we are getting satellite imagery. Unfortunately, Venus and Sentinel-2A, 2B don't give us thermal images, and we want that thermal images, at least for the time being. So we're having to interpolate thermal imagery from Landsat 8, that's 30 meters. We're having to use mathematical algorithms to downsize those images. And the reason we want to use aerial and UAVs is to validate our downsizing algorithms. Now, when EcoStress is launched, it will have a thermal image. But the 2 we're using now, primarily Sentinel-2A, 2B, and Venus, only have multispectral images. I think that's all I have to say today. If I have any time, I'll answer any questions. Yes, sir.
When you're doing these leaching studies, where you had these down to 90 and 120 centimeters, right?
Yes.
You were checking down to 8, right?
I'm sorry?
You were checking down to 90 and 120.
Yeah, 120, 4 feet. That's 4 feet.
Okay. So what was the soil type in there? Do you have
Oh, it changes. This is an alluvial valley, and the paramaterial for our soils is silt that the river deposited it before it was dammed out. But the depth varies. Even within a field, sometimes it's 2 feet, sometimes it's 3 feet. Sometimes we have silt all the way to 4 feet. But most of the time on average, and I hate to throw an average because it's so variable, but in average, we generally transition into sand at about 2 feet. So you have 2 feet of silt over sand, but like I said, sometimes it's silt all the way down. Sometimes there's only a foot of silt over 3 feet of sand. But if you punch holes in these soils, the average is probably there's 2 feet of silt over sand. Does that answer your question?
Kind of. Well, the reason being is that every time there's a soil transition there, I was wondering if you were working in
Oh, we're not working in a particular spot. Those bar graphs I showed you are the mean of several samples that were for which the sites were statistically determined from the conductance survey. So some of those samples are 1 foot over sand, some are 4 foot, some are, so that mean is a statistically selected mean. We've taken every effort to avoid bias. So we're confident in that mean, and we don't have to look at that mean in the bar graph because I have whole maps of the whole field. I've plotted out whole maps. Anything else? Thank you. Oh, yes, sir.
I'm seeing that test of drip irrigation in the region, and how do you think that will impact
Drip is not sustainable in our climate unless you can leach with surface water once in a while. I have another project. It's not related to YCEDA. It's drip irrigated off in the Imperial Valley. Those ECs are already up to 8. That's not sustainable. And unfortunately, the grower did away with all his surface irrigation infrastructure. He can't put a flood irrigation on. In desperation, what he finally did was put solid sets out there after his last cutting in November, his last dairy hay cutting in November, and ran the sprinklers until his first dairy hay cutting in early January. So he tried to leach the crap out of it with sprinklers the best he could, but he has no surface irrigation conveyance system anymore. So you could say, and I say it confidently, in our climate with our ET, drip is not sustainable without flood irrigation. Thank you. Yes, sir.
If we do lettuce, we follow that up with wheat, and we're doing a salt load with both, is 1 flat water sufficient to push that salt down?
It'll push it out of the top foot, but it's there in the second foot, and hopefully some of those other irrigations will move it out. Now, I'm not ready to commit that wheat is universally salt loading, but 2 out of the 3 sites I have that are more typical of our soils, it is. And I think part of it is we're underestimating ET of wheat because we discontinue our data acquisition when the crop starts to senesce. But in the meantime, till you get out and combine, you have 1 billion straws out there conducting water from the soil reservoir up into the atmosphere. And even after the wheat's combined, till you can get out there and ditch, there's still straws out there, shorter straws. So I think we're grossly underestimating the water that's transmitted through a wheat crop. Did I address your concern, or kinda? Okay, well, thank you all.